VIT, a place to learn, a chance to grow.
Hello friends, welcome back to this short lecture series on process dynamics and control. In this lecture, we will cover the mathematical modeling of linear processes, and we will take examples from single input single output case and multi input multi output case for developing the mathematical model and simulate them using SIMULINK for analysis. To start with, let us see why we should develop the mathematical model. The basic task for a process engineer is to study the behavior of the process under the influence of manipulating variables and disturbing variables. And also, based on the behavior of the process, the engineer has to design the controllers to achieve the desired performance. This design and analysis could be done with the help of experimental approach, but this approach requires the physical presence of the process, the entire process. And also, it requires a lot of experiments to be conducted on the process, which is quite costly and time consuming. We have to make sure nothing is going wrong while doing all these tests. Whereas in theoretical approach, we are going to represent the system with a set of mathematical equations, and we just need a simulator to simulate all these equations for design and analysis purpose. And we will be building these mathematical models uh, based on our requirements and also based on the process behavior. When we are interested in analyzing the dynamic behavior of the system, we will be building the mathematical models with the help of ordinary differential equations. Whereas algebraic equations are used for analyzing the steady state behavior of the system. The fundamental models are built with the help of mathematical equations based on the relationship of the variables present in the system. And empirical models are built with the help of experimental data available if the process is already existing. And based on the nature of the process, we'll be building lumped parameter models and distributed parameter models. So lumped parameter models are built if the system variables are changing with respect to time only. Whereas if the system variables are changing with respect to time and space, we will be building the distributed parameter models. For characterizing a system and its behavior, we need state variables which describe the natural state of the process at any time, and state equations which describe how the natural state of the system changes with time. And these state equations relate the state variables which are dependent variables to other independent variables present in the system. And these state equations are derived from application of conservation principle on fundamental quantities. So this is the principle of conservation, which defines the accumulation of S within a system over a period of time, which is equal to flow of S coming into the system over a period of time subtracted by the flow of S going out of the system over the period of time, plus if there is a generation inside S and consumption, these two terms also coming into the picture. So generation of S within a system over a period of time minus consumption of S within a period system over a period of time. So this S represents the fundamental quantity in the process. So according to the process, this capital S could be total mass or mass of individual components or total energy or momentum. Now we will take an example for a single input single output case from a liquid level system. Now in this case you can see we have a cylindrical tank which is getting an inlet and there is an outlet, and at the outlet we have a linear valve, and this valve is related to the process variable which is liquid level in this fashion. And we are making a small assumption that the density is constant. So if it is a chemical involved, there may be variations in the density. Let us assume we are working with water initially, so we can take density changes are negligible. Right. Now we'll see how to develop the mathematical model for this. Now if you are taking the conservation principle, which states accumulation of the fundamental quantity capital S within the system. So in this case we are building the mass balance equation, that is the capital S which you saw in the previous slide is going to represents total mass in our case. So we are trying to write the mass balance equation. So the total accumulation of mass over a period of time is represented here. So rho capital A, which is cross-sectional area of the cylindrical tank, and dH by dt, how this parameter changes with respect to time, which is equal to, so there is something coming in. So there is an inlet. So rho I Qi is the input coming into the system over the period of time, and then minus flow of S out of the system. So the outlet is here. So rho naught Q naught, and we have a relationship between this Q naught and the valve resistance. So if I am writing this, this is the ODE equation for the system. So we can analyze the dynamic behavior of the system here. Since this system is linear, we can represent this ordinary differential equation with the help of transfer function also by taking the Laplace transform. So we'll be getting this. So where the process output is h of s, we are interested in monitoring the liquid level changes. Where the the input is inlet flow of the liquid. So this could be represented as R by ARS plus 1. So since it is a linear system, we can represent with the help of both ODE equations and transfer functions. Now we will see how to simulate this single input single output case using SIMULINK and get the dynamic response analysis. So the ODE model is already available. So dH by dt is a function of input flow and the process variable level, and we also have the transfer function model also. So now we are going to simulate this in SIMULINK have a blank model open. First we will see how to build this using basic Simulink models. So first starting with the integrator, and the input for the integrator is the dx by dt, and the output will be h in this case. So it's a good practice to start ODE simulations from the integrator. So the integrator is ready. Now our objective is to observe how the process variable is changing. So I'm connecting this integrator output, which is the process variable, to the scope, and then we are taking a input for this setup. So the input for our single input single output case is a flow rate, so qi, and if you're going back to the model, this dh by dt is a function of qi and h. So qi minus h divided by 0.1, so which is the valve resistance according to the modeling. So we have to now simulate this qi minus h by 0.1. Going on to the model building, for getting this h by 0.1, selecting the gain block and rotating the block, and then we'll modify the block parameter, and the gain here is 1 by 0.1 because I need h by 0.1. We can connect the input for this gain block, which is coming from h. So now h by 0.1 is ready. Now I have to get qi minus h by 0.1. For this we need the subtractor. Again, this is available in the math operations library. So qi minus h by 0.1 is ready here, and now we have to divide this by a according to the model. So cross-sectional area is 2 meters square, so I have to again include a gain block with value 1 by 2. So another gain block is added, and the gain value is modified as 1 by 2. Now this is what this dh by dt is. So qi is the input, h is the process variable. So we got the model done, 1 by 2 qi minus h by 0.1. The process model is done. Now to modify the input according to the problem statement, the step time is 0. At 0th instant the input is given, which is having a magnitude of 1. Now with the default simulation parameters available in SIMULINK, we can run the system. So to see the dynamic response, if you open the scope, you can see the level changes from 0 to 0.1 and settles there. So this is the dynamic behavior of the system when we are giving a step input in the flow rate. Now we will see how to simulate the same setup with the help of transfer function model which we have already. Since it is a linear system, we can convert this ODE equations into transfer function model using Laplace transforms. So for taking the transfer function, we are taking the block from the continuous library and modify the block parameters according to the process model. 0.1 divided by 0.2s plus 1. Now this is the transfer function model. What we have above is a ODE model built with the help of basic Simulink blocks. Now for this transfer function model, we will give the same input which we used for ODE equation, and then we will add a scope to observe the response. And if I run this again, both scopes, if you are observing, will give you similar dynamic response because both the systems are the same, one with ODE and another one with transfer function model. This way you can simulate and analyze the single input single output case using. Now we will take a multi-input multi-output case and we'll see how to write the mathematical equation. So in this interacting tank setup, we have two inputs. We have input 1, input 2. So first input is going as a inlet flow for tank number 1, and second input is the input flow rate for tank number 2. And we have interacting system here, and there are valves connected at the outlet, and all these valve resistances are related to the liquid levels and the corresponding flow rate through the valves. And we have two variables here, H1 and H2. So two state variables and two inputs. So when I write the first equation, so this is representing the tank 1. So this ODE equation is for tank 1. So which defines dH1 by dt is equal to 1 by A1 multiplied by Qin is the input coming in to this tank minus whatever is leaving here. So since it is an interacting setup, so this flow rate will be H1 minus H2 by R2. Minus there is another outlet here which is H1 by R1. And again here we are assuming the density is constant. So you can see there is no density term involved in writing the ODE equation. And we have another variable here for dH2. So the second ODE equation is written based on tank number 2. Here we have input coming from the inlet flow Qi2 plus we have an inlet here coming through valve R2. So this is also inlet now. So plus H1 minus H2 by R2 minus we have an outlet through third valve, so minus H2 by R3. So this way you can write the ODE equations for multi-input multi-output case. Now we will take an example for this multi-input multi-output case and we will see how to simulate them using SIMULINK, like the way we did for single input single output case. So these two ODE equations, already I have developed the SIMULINK model using basic blocks, where we have the integrator taking dh1 by dt as inputs, and similarly dh2 by dt as input for the second integrator, and we have h1 by r1 term and h1 minus h2 by r2 term, and this uh, second integrator has taking this dh2 by dt as input, and the second equation also we have this h1 minus h2. And for the first equation it is having a subtraction sign. For the second equation it is having the addition sign, because the flow rate considerations, the direction of flow is considered in the modeling. And the process inputs, according to the problem statement, the first tank inlet gets the step input at 0 time, whereas the second tank gets the input at after 4 seconds, but both of them are getting a magnitude of 1, and we will run this simulation with the basic SIMULINK settings available, and we can observe both the process parameters, that is tank 1 and tank 2 on a single scope. So if you are pressing this auto scale, you can see the response. Since the first tank gets the input first, there is large change in level 1, and then the second tank gets large input after 4 seconds. So you can see large change in level 2 after 4 seconds, where it is minimum in tank 1. So this way you can simulate the multi-input multi-output case using basic blocks available in SIMULINK. Now the same problem statement we will try to simulate using a differential equation editor. For this, go to command window and type DEE. This will open the differential equation editor window. So you have to take this differential equation editor to your model building environment, and then we can go into the block and modify the parameters. So now on a empty SIMULINK model, I'm putting this differential equation editor, and now you can see there is no inputs, no outputs in the block. It is just a rectangular block. Now you can include the number of inputs available in your simulation. Now I have two inputs, flow rate in tank 1 and tank 2, and then you can write the equations. So all the inputs will be represented with u's, and all the system variables will be represented with x. So u1 is the first tank's input minus, so x of 1 is level 1 and x of 2 is level 2. So in the model equation we have x1 minus h1 minus h2 divided by r2. So those parameters maintained now. Then minus, we have another outlet h of 1 divided by r1. So the whole thing is divided by cross-sectional area of tank 1, which is a1 in our case. So initial value of x of 1. So the first equation represents the dh1 by dt, which is x1 dot. So level 1's initial case also we have given here. Now the second equation, where the input is level tank 2's input is inlet flow rate, plus this h1 minus h2 divided by r2 is input for this tank. So there is a plus sign, h1 minus h2, and then minus, there is outlet through valve 3, so minus x of 2 by 0.1. The whole thing is divided by cross-sectional area of tank 2. Now this initial case for level 2 also 0. Now the output equations, since we are interested in observing both level 1 and level 2, x of 1 and x of 2 both are part of this output equation. Now you can see the number of inputs and number of outputs updated in the block we initially developed. So according to the output equations, two outputs are there now. According to the inputs you gave, we have two inputs. Now we can take other basic blocks for step input and scope for monitoring. Then we can simulate the system. So I have two inputs. So both the inputs I have to configure according to the problem statement. And then we have to monitor the tank outputs. Let me change the parameters for the scope so that I can monitor both of them in a single scope. So I'm increasing the access to 2 so that both outputs I can see simultaneously. Now after connecting this, you can go to step time 0 for inlet flow rate 1, and for the second tank's inlet flow rate the step time is 4, but the magnitudes are same again. If you are running this, you can observe how level 1 and level 2 are dynamically responding to the inputs. Again you can see the similar response we are getting what we got for basic Simulink blocks. Level 1 and level 2 changes according to the flow rates we gave. So this way you can simulate the system with the help of differential equation editor, which reduces the number of blocks present in your model environment. So these are the references used for this lecture. If you have any clarifications or corrections,